Euler angles. We mentioned that Euler equations tend to be tricky with torque because they use body frame. Another approach is to use so-called Euler angles, angles that are defined with respect to space inertial frame of reference. We will denote the three angles as phi, theta, and psi. There exist several recipes for doing it. We will stick with one of the common recipes of how to find these angles. Our job is, through series of rotations, to orient our body beginning from its first aligned with respect to all of its principal axes with the space reference frame axis x, y, and z. X, y, z are space axes, and we will first align our body principal axis with them. In fact, E1, E2, and E3 axes will generally not be the same as x, y, and z, and we will denote it by primes. So we are hoping through several rotations, so there's E1 double prime, E2 double prime, and E3 prime, just one prime, as you'll see why shortly. We hope through a series of rotations to move these three vectors, these principal axes, into the final orientation, which of course is just E1, E2, and E3, to orient our body in a way that we want it oriented, this arbitrary orientation. Well, turns out that we can accomplish an arbitrary orientation of our body through three Euler angles. These three angles, phi, theta, and psi. In the first step, we define angle phi. We start with E1 double prime parallel to x, E2 double prime parallel with y, and E3 prime parallel with z. Next we rotate around z-axis by angle phi. So that we get the new orientation of E1 prime, and this angle here will be angle phi, as well as getting the new orientation of E2 prime. We continue with the second step, step B, which defines theta angle. Now we have the following temporary basis: vector E2 prime from the previous step, and we choose to rotate around this vector by angle theta. We rotate around axis E2 prime so that angle theta, this angle here, gives us a new orientation of E3 vector, which now happens to be aligned with the actual orientation of E3 vector of the body. And so now we have a new vector E1 prime, E2 prime, and E3 without any prime. The last step, step C, where we will perform orientation around the newly found vector E3. So here's our previous three vectors, E1 prime, E2 prime, and E3. And we perform a rotation around E3 so that the new vector E2 without any prime becomes aligned with the desired orientation of this principal axis. And we will have vector E1 without any prime defined as well. So with these three steps, we can always ensure that we can rotate our body with respect to the space frame and orient it with the desired orientation of our rigid body. In order to use Euler angles, we have to find some additional relationships. We need to find a relationship for omega and relationship for angular momentum in terms of Euler angles. We know that angular velocity can be expressed in terms of three components, each corresponding to the steps that we performed in order to find Euler angles. Step A plus omega corresponding to step B plus omega corresponding to step C. Since angular velocity is just a vector, we can use addition. What we know is that for angle phi, the angular velocity corresponding to it will be phi dot, and then the direction along which this rotation was performed was axis z. Second, we can add theta dot to the angular velocity, and the vector along which we define this rotation was given by E2 prime. And lastly, psi dot, and the direction along which this rotation happened was E3. The general case tends to be rather messy, but it simplifies greatly if we consider symmetric top. We consider symmetric top, which has lambda 1 equal to lambda 2, but lambda 3 is different. In this case, we don't have to follow all the three steps in our recipe. It is sufficient to only follow two, since the principal axis, E1 and E2, can be chosen arbitrarily as long as they are perpendicular to E3. We'll take that advantage, and we will simply use E1 prime, E2 prime, and E3. So we will allow arbitrary orientation of E1 and E2 as is most convenient for us. The only vector that we really need to get right is E3. So if we consider our coordinate system, the space coordinate system, and then orientation of vector E3 given by angle theta, and then we consider E1 prime, which is perpendicular to E3, we can write space axis z unit vector in terms of vector E1 prime and E3. We can see that in order to combine these two vectors, we have to multiply them by trigonometric functions of theta. For the first one, we get minus sine theta, as you can see from this diagram. And then for the second vector, we have to multiply it by cosine theta. And this way, we can write omega in terms of the basis E1 prime, E2 prime, and E3, it will have the following. Rotation due to phi dot will go via sine theta and a minus sign into E1 prime using this expression above for z hat, but it will also go into component E3, part of it, via cosine theta. Then rotation due to theta dot goes with E2 prime, and rotation with psi dot and phi dot cosine theta goes into E3 vector. This term here, cosine theta, comes from the expression cosine theta above. Thus we get the following useful result, now in terms of Euler angles, that omega and angular momentum in basis E1 prime, E2 prime, and E3 will be given by the following coordinates. Omega will be given by minus phi dot sine theta, then theta dot, and lastly psi dot plus phi dot cosine theta. And then for L, we have the same components but now multiplied by principal moments, lambdas, minus lambda 1 phi dot sine theta, lambda 1, because lambda 2 and lambda 1 are the same, theta dot, and lambda 3 times psi dot plus phi dot cosine theta. Now we can use these expressions of omega and L in terms of Euler angles that are defined with respect to inertial or space frame.